Every time you ask an artificial intelligence to write an email, summarize a document, or generate a piece of digital art, you are activating a physical chain reaction. A single search query processed through a large language model consumes roughly 10 times the electrical energy of a standard Google search. It also drinks water, nearly a small bottle's worth, to cool the humming silicon chips located hundreds of miles away from you. We have been conditioned to view the digital revolution as an ethereal, weightless transition. We talk about the cloud as if our data exists in a serene, atmospheric layer above the Earth. But this is a carefully constructed illusion. In reality, the cloud is not weightless. It is remarkably heavy. It is built from concrete, cooled by millions of gallons of fresh water, and powered by high-voltage transmission lines. And right now, this digital infrastructure is colliding head-on with a hard physical boundary: the aging electrical grids of the modern world. We are attempting to build the future of intelligence on a power grid designed in the mid-20th century. The world's most advanced software is now entirely bottlenecked by the world's most primitive physical assets: copper wires, heavy steel, and thermal coal. Understanding this collision between digital ambition and physical reality requires a systematic way of looking at the world. The media often paints a binary picture. Either AI is a miracle that will solve all our problems, or it is a speculative bubble. The truth, as always, lies in the underlying logistics, resource flows, and structural limits that rarely make the front page headlines. To truly understand these complex dynamics, you have to look past the surface-level narratives. To understand the scale of the impending bottleneck, we must look at the fundamental physics of the grid. An electrical grid is not a reservoir where energy can be stored for a rainy day. It is a real-time zero-sum balancing system. At any given millisecond, supply must precisely match demand. If that balance wavers, transformers fail, generators trip, and entire regions come dark. Into this delicate balancing act steps the modern AI data center. A traditional data center processes predictable bursts of traffic, emails during work hours, streaming video in the evening. But an AI training facility is entirely different. It runs at near constant, maximum capacity for months at a time, 24 hours a day, 7 days a week. This represents what grid engineers call baseload demand. To meet this demand, tech companies cannot simply rely on solar panels or wind turbines. Solar power only works when the sun shines. Wind power drops off during calm weather. AI training runs cannot tolerate these micro-interruptions. Sudden drop in power can corrupt months of computational progress, costing millions of dollars in lost time. Therefore, AI requires continuous, uninterruptible power. And this is where the physical reality of our energy transition becomes problematic. Across the Western world, traditional baseload power plants, coal and nuclear, are being decommissioned. They are being replaced by intermittent renewables. We are increasing our reliance on variable energy sources at the exact moment we are introducing the most relentless, continuous power consumer in human history. But the challenge is not just generating the power, it is moving it. This brings us to the humble electrical transformer. These massive oil-filled metal boxes are the vital nodes of our infrastructure, stepping voltage up for long-distance travel and stepping it down for local consumption. Currently, the global supply chain for these transformers is in a state of paralysis. A standard high-voltage transformer requires specialized electrical steel, hundreds of miles of copper wiring, and highly skilled manual assembly. Before the AI boom, the lead time to order a major transformer was roughly 6 to 12 months. Today, that lead time has stretched to 4 years. Even if we could generate all the electricity the AI sector demands, we physically cannot build the grid infrastructure fast enough to deliver it to the servers. The digital revolution is running out of copper. This logistical bottleneck is not just an engineering puzzle, it is a geopolitical vulnerability. The race for artificial intelligence is the defining geopolitical contest of the 21st century. The nation that controls the most compute capacity will inevitably dictate the global standards for defense, finance, and industrial automation. Currently, this race is a duopoly between the United States and China. But both superpowers are facing entirely different physical constraints. The United States holds the world's most advanced software ecosystem and the largest concentration of data centers. However, its electrical grid is highly fragmented, privately owned, and notoriously slow to upgrade. Regulatory hurdles and localized resistance mean building a new transmission line in the US takes an average of 10 years. China, by contrast, operates under a centralized command economy. When Beijing builds a data center cluster, it constructs the transmission lines and power stations to support it simultaneously. While China is installing massive amounts of solar and wind capacity, it is also building coal plants at a rate of 2 per week to guarantee baseload reliability for its industrial and technological sectors. In the West, tech companies are desperately trying to bypass the traditional grid altogether. Consider Northern Virginia's data center alley. This single geographic cluster handles an estimated 70% of the world's daily internet traffic. The local utility, Dominion Energy, has warned tech companies that its transmission lines are reaching their absolute thermal limits. Unwilling to wait, tech giants are bypassing public utilities and buying the power plants outright. Microsoft recently signed a 20-year agreement to purchase 100% of the output from a resurrected nuclear reactor at 3 Mile Island, the site of the worst crucial nuclear accident in U.S. history. Amazon Web Services purchased a massive data center campus in Pennsylvania built directly adjacent to the Susquehanna nuclear power station, drawing electricity directly from the reactor before it even touches the public grid. This is a fundamental shift in corporate behavior. Tech companies are transforming from software developers into industrial energy barons. They are cannibalizing the very clean energy assets that were supposed to power our domestic green transition. This private capture of energy infrastructure has profound consequences for the rest of society. When a tech giant buys a nuclear plant's entire output, that power is permanently removed from the public grid, forcing reliance on older, more expensive fossil fuels. The result is a direct transfer of cost from Silicon Valley to everyday citizens. In places like Ireland, data centers now consume more electricity than all urban households combined. The Irish National Grid operator has warned of potential rolling blackouts, forcing regulators to implement strict moratoriums on new data center connections. In the United States, utility companies are already revising their 10-year demand forecasts upward by orders of magnitude. To meet this unexpected surge, utilities must invest billions of dollars in new gas-fired power plants and transmission upgrades. Under current regulatory structures, these multi-billion-dollar capital projects are not paid for by the tech companies. They are socialized. They are added to the monthly utility bills of average homeowners. We are approaching a point of deep systemic friction, a point where citizens must choose between cheaper home heating or faster algorithmic processing. We've spent the last 3 decades believing that technology had liberated us from the physical constraints of the earth. We believed that code was infinite, that scale was cheap, and that intelligence could be generated out of thin air. That software cannot escape hardware, and hardware cannot escape the laws of thermodynamics. Every calculation requires a state change in a physical transistor. Every state change releases heat. Every watt of heat must be dissipated by a cooling system. As we push deeper into the age of artificial intelligence, we are discovering that the virtual world is merely a shadow cast by our physical infrastructure. If we want to build a world of infinite digital intelligence, we must first master the finite, heavy, and stubborn mechanics of the physical grid. Otherwise, the digital revolution will simply burn itself out. If you want to understand the physical realities shaping our global future, make sure to subscribe. Thank you for watching, and we will see you in the next breakdown.